This is my circuit.
In the first stage, we will be using IC1A, which is ICTL072, a dual low noise JFET, a junction field effect transistor, an input general purpose operational amplifier. It produces a low supply of voltage, around 10 millivolts to 1 volt, but it does not provide any current. It is a fixed gain, closed loop, non-inverting operational amplifier. The operational amplifier will amplify the sound, causing the sound to be either be subtracted or added. The signal coming from the electric microphone needs to be brought up to a certain level needed for the line input by the circuit. Capacitor C1 acts as a coupling capacitor at 10 microfarads, isolating DC voltage bias from the input. Below this in the schematic, resistors R5 and R6 acts as a voltage divider with 10 ohms each, providing half of the supply voltage, which will supply the op-amp to work at a single supply mode at 4.5 volts. The formula will be R6 over R6 plus R5 multiplied with VCC. VCC will be supplied at 9 volts, while R5 equals to R6, which is equals to 10 kilovolts. The final answer will be 4.5 volts. Resistors R2 and R3 and capacitors C2 and C3 forms the bandpass filter, combining a low-pass and high-pass filter. Low-pass filters allows low-frequency signals to pass through while attenuating high-frequency signals. On the other hand, high-pass filters allow high-frequency signals to pass through while attenuating low-frequency signals. This allows only a specific band of frequency to pass through while rejecting all other frequency. The formula for passband gain is ACL equals to 1 plus R2 over R3, substituting it into 1 plus 220 kilo ohms over 10 kilo ohms. The final answer will be equals to 23. Capacitor C4 acts as a coupling capacitor, coupling the output of IC1A, the first op-amp, to the next segment. In the event any DC input offset were amplified, there will be a larger output offset, causing the output to be too large and reducing headroom. This causes the output waveform to be cut. C4 will isolate DC signals and allow AC signals to pass through. Based on the table for stage 1's amplifier, as the frequency increases, the gain will increase alongside it at a maximum of 23, which was what I calculated just now. The maximum frequency will be 100 Hz, and the frequency above 100 Hz will cause the gain to drop. The maximum gain I got was 21.2, giving me 26.5 decibels. On the frequency response curve, the minus 3 decibel line will be 26.5 decibel minus 3 decibel equals to 23.5 decibel. Using a ruler at 23.5 decibel, the low frequency will be at 25 Hz, and the high frequency will be at 1.2 kHz. To find the bandwidth, use a high frequency to minus the low frequency, 1.2 kHz minus 25 Hz, giving me 1175 Hz. Since a single supply mode will cause the negative side of the waveform to be cut, the voltage divider is the level shifter. This will allow it to shift the entire waveform upwards, causing the waveform to not be cut. At stage 1, first set power supply DC source to 9 volts, and then connect the clips from the power supply to the circuit. Do not connect the green clip. Second step will be to set the function generator frequency to sine wave at 10 Hz 200 mV peak to peak. The result will show the output to be 1.36 volts. Output will be 2.36 volts at 15 Hz at 200 mV peak to peak. I'll get 2.84 volts at 20 Hz at 200 mV peak to peak. I'll get 3.68 volts at 40 Hz at 200 mV peak to peak. I'll get 4.24 volts at 500 Hz at 200 mV peak to peak. By 800 Hz, I'll get 3.84 volts due to the gain causing it to decrease. At 1000 Hz, the output will continue to decrease to 3.48 volts. At 2k Hz, I'll get 2.4 volts. Lastly, I'll get 1.38 volts at 4k Hz. For the second stage, we'll be using IC1B, which shares the same IC TL072 with IC1A. It is a negative feedback loop amplifier, where a fraction of the output is subtracted from the input. It is then returned back to the input with a phase inversion 180 out of phase. Resistors R9 and R10 acts as a voltage divider, each at 10k ohms, and are connected to pin 5 of IC1B. To find the VDR, it is equals to R10 over R10 plus R9 times VCC, which the VCC is at 9 volts. The answer will be equals to 4.5 volts. This will allow the operational amplifier to work as a level shifter and as a single supply mode. This will allow the output to not be saturated. Trimmer P1 will then control the feedback signal, reducing the gain of the amplifier, which will not saturate the output voltage, and this will allow it to act as a linear circuit. For stage 2, channel 1 will be connected to TP2. The frequency and power supply will remain the same, and then connect channel 2 to TP3. After placing everything where it should be, the result of the output voltage will be around 5.44 volts. By adjusting trimmer P1, the output waveform will change. The waveform will be amplified, but will be saturated and cut off at a certain point. At stage 3, capacitor C5, which is 10 microfarads, will act as a coupling capacitor, blocking out DC signals and allowing AC signals to pass through. Resistors R11 and R12 will act as a voltage divider at 10k ohms each. The formula will be R12 over R12 plus R11 multiplied with VCC. VCC will be supplied 9 volts, giving me an answer of 4.5 volts. The voltage divider will allow this to act as a single supply mode and a level shifter to make sure the output is not saturated. At stage 3, IC2A, which is ICTL072, is the same as IC1A and IC1B. IC2A is a Salient key second order low pass filter formed by two low pass resistor capacitor network. Capacitor C7 at 10 nanofarads will provide the feedback for shaping the response near the edge of the pass band. This will allow low frequency to pass through while filtering out high frequency. Output voltage of pin 1 of IC2A will pass through C8 at 10 microfarads to filter out any DC signals, acting as a coupling capacitor. The low frequency will be 0 Hz, and the high frequency will be equal to the cutoff frequency. To find the bandwidth, we'll use the high frequency minus the low frequency, which will be the same thing as using the cutoff frequency to minus 0 Hz. This will give me cutoff frequency. The cutoff frequency formula will be 1 over 2 pi square root R7, R8, C7, and C8. By substituting the values in, it will be 1 over 2 pi square root 22.6 kilo ohms times 22.6 kilo ohms times 10 nanofarads times 5 nanofarads. Based on the table, it shows that below 500 Hz, the gain is near unity gain. But as the frequency increases from 500 Hz, the output voltage as on the frequency response curve, the minus 3 decibel will be minus 0.45 decibel minus 3 decibel equals to minus 3.45 decibel. The low frequency is 0 Hz and the high frequency is 950 Hz. The bandwidth will be 950 Hz, which is quite near the cutoff frequency that was calculated just now. At stage 3, leave the power supply at 9 volts and set the clips from the power supply to the circuit without connecting the green clip. Second step is to set the function generator frequency to sine wave at 20 Hz, 5 volts peak to peak. The output result will be 4.72 volts. I'll get output voltage of 4.8 volts when I set the function generator to 50 Hz at 5 volts peak to peak. At 100 Hz, I'll get 4.72 volts for the output voltage. At 500 Hz, I'll get 4.56 volts for the output voltage. But at 800 Hz onwards, the voltage output will drop substantially, giving me 3.92 volts. At 1000 Hz, the output voltage will be 3.12 volts. I'll get 2.52 volts for the output voltage at 1.2 kHz. I'll get 1.84 volts at 1.5 kHz. Finally, at 4 kHz, I'll be getting 0.26 volts for the output voltage. At the final stage, IC3, which is LM386N-1, is an audio amplifier that will drive a speaker. It is working in a single supply mode internally. Thus, there is no need for a voltage divider. To power up the speaker, current will be needed to be driven in. At the output of pin 5 at IC3, capacitor C15 will filter out high frequency that is above 40 kilo ohms. This is to ensure that the output waveforms remain stable. Capacitor C13 at pin 5 of IC3 will act as a coupling capacitor, isolating DC signals and allowing AC signals to pass through. The input from TP4 will pass through trimmer P2 at pin E, which has full amplitude, while pin A and S has zero amplitude of the input waveform. At stage 4, connect channel 1 to TP4 and channel 2's probe to the oscilloscope to TP5, leaving everything untouched. After placing the probes at where they are supposed to be, the power supply will be at 9 volts, frequency at 20 Hz, and amplitude at 5 volt peak to peak. The output voltage will be around 6.6 volts. By adjusting trimmer P2, the output of TP5 will change. It will become saturated, but the final output will be the maximum sine wave attained without being saturated.